Sorry guys, I hit the wrong button. Okay, so going back. So increasing the temperature of a system by a specific amount of temperature, like if I'm thinking about a system, if I increase the system, let's just say by a little bit of a higher temperature that we'll just call T, then ultimately what's going to happen is we know that energy is going to be transferred from either from the hotter object to the cooler object. So whether that be system to surroundings or surroundings to systems, if I increase temperature, then I know that the temperature is going to be transferred one way or the other. Now, if the system, or if temperature is infinitesimally small, it's so small that ultimately I don't really see a big transfer of energy changing in between, or of heat flow in between systems and surroundings. A lot of times we think about reversible processes as being that way. So let's give a different definition of a reversible process. And that is, a reversible process is where the system can change in such a way that the system and the surroundings can be put back into their original states by exactly reversing the process. Sometimes we don't think about... easy example. Let's just go with an easy example. I can easily change liquid water into ice by putting it in the freezer. Or I can easily reverse that process and get the water back by changing the ice that I just made and put in the freezer and leaving it out at room temperature, just raising the temperature, and now getting liquid water. So ultimately what's happening is there's no net change to either the system or the surroundings. So I can raise the temperature and have heat changing from surroundings into the system, or I could lower the temperature and then have some of that energy moving back out into the surroundings. So ultimately, if I'm doing the exact same thing and I think about I'm starting off with a certain amount of energy, but then at the end, so in A, maybe I'm losing a certain amount of energy, but then here in B, that system is gaining that same amount of energy back, the net change is really going to be nothing at all, because it's just like they're opposites, equal in magnitude, but opposite really in direction of their heat flow. An irreversible process is going to be different than this. An irreversible process is something that cannot be undone by just exactly reversing that original change to the system. So I want you to think about, go back and think about that egg that's being dropped, an irreversible process. I drop an egg on the desk or on the ground. I can't go back and reverse that exact system that I first started off with. I can't reverse that change. So I can't just magically get that yolk to get back in the egg and the egg to no longer have the cracks in it to where I can have that system back over again. So spontaneous processes, what we have found, that spontaneous processes are typically irreversible. Spontaneous processes are irreversible. Now, on this picture, we can think about also an irreversible process. We have an expansion of an ideal gas at constant temperature. Also remember that constant temperature means that it's an isothermal process. Constant temperature, isothermal process. Iso meaning like equal, and then thermal meaning temperature, so it's at a constant temperature. So in the cylinder piston arrangement, so I just have a piston here. So at this side, I have the piston, and it's able to move. I have a movable partition here. I'm able to move this partition. I have half of it with gas. I have half of it filled with a vacuum. Let's say that I move this partition. I know then that the gas is going to start to spread out into the vacuum. I see that here. I've lifted the partition, and now I have this gas that's now expanded into this piston. This is an irreversible process. It's an irreversible expansion. And it's an irreversible because if I put the partition back, all of a sudden, just because that partition moves back, does that mean all of those gas particles are going to suddenly move all the way back over here to form the exact same thing? No, they're not. It's not going to happen unless I move this piston and do work on the system by moving this piston down and creating that same amount of gas and creating that same volume that I originally had over here. So here's my piston. Let's just go back. Here's my piston. I have gas particles that are separated from a vacuum. So I have half of this is a vacuum, half of this is gas. I have this movable partition here in the middle. I lift that partition. That gas is going to spontaneously move to fill that entire volume. And that's an irreversible process. It's spontaneous. It's going to happen. But if I move that partition back just the way that it is, it's not like all of a sudden those gas particles that moved over here aren't going to spontaneously by themselves move back over in half of the side and leave the other half as a vacuum. I can't do that. Instead, I'm going to have to apply some amount of work. And that work is going to be by changing the volume. So I'm going to decrease the volume and increase the pressure to get that original gas back, to create that empty space over here and to get that gas back the way that it was. And then it's like that partition was there to begin with. But I couldn't have done that just by reversing the system the way that it was before. So this is just an example of an irreversible process. Guys, we've talked about entropy before. Entropy we know is just really just as associated with the extent or randomness. It's the extent of disorder. So it's the distribution of energy among the various motions of the molecules of the system. That's one definition. Or it's just this extent of disorder. So something that has a lot of disorder is high in its entropy. And we will symbolize entropy with an S. Entropy was first coined by scientist Rudolf Clausius, and that happened kind of in the 19th century. My question, I guess, for us is, how can we relate entropy changes to heat transfer and to temperature? How does entropy relate at all to heat and to temperature? Clausius developed kind of a way to figure out how entropy was related to heat and how it was related to temperature. So for him, he decided that there was a ratio of heat that was delivered and the temperature at which it was delivered. So remember, we just symbolize heat as Q and temperature as T. So again, let's just keep going with this. Clausius says, my change in entropy is going to be proportional to, it's going to equal the amount of heat, the ratio of heat that I have over the temperature that we have of a particular process. So for a process that's occurring at a constant temperature, we just said that's the same thing as an isothermal process. The change in entropy, change in delta S, change in entropy is going to be equal to the heat that would be transferred if the process were reversible divided by that particular temperature. And this is just one possible way that we could calculate change in entropy. So kind of like what we talked about before in chapter 5 with total energy as E or enthalpy as H, we could figure out the change in entropy by saying, okay, what's the final entropy minus the initial entropy? And that will give us our change in entropy. So we have a hard time finding out, well, what's the final entropy and what's the initial entropy? It's really hard for us to calculate that in a lab. Instead, Clausius says, okay, we can easily calculate temperature, or we could experimentally measure temperature. We can also experimentally measure the amount of heat that we have in a reversible process, or the amount of heat that's produced, or the amount of heat of transfer. So I know Q, I know T. I can also say, Clausius is saying, let's say that ratio is going to be equal or equivalent to the change in entropy. Okay, so if we're looking at this example here, actually, I want to hold off on this, guys. Let's do this problem together in class on Friday. So remind me, what slide is this? Slide 11, let's do in class. Slide 11, we're doing in class. Okay, second law of thermodynamics is about entropy. So all of this stuff in this chapter is really focusing on entropy right now. And entropy is just the state of disorder. So the second law of thermodynamics states, the entropy of the universe increases for a spontaneous process. Guess what? In a spontaneous process, we're going to have more disorder. Things want to move toward disorder. So entropy of the universe does not change. Another way of saying the second law of thermodynamics is saying that the entropy of the universe does not change for reversible processes. So entropy of the universe, everything wants to move towards disorder. And spontaneous processes are irreversible processes, meaning that let's go back to the egg. I drop an egg. It was a solid. Now it's shattered into yolk, into all of these different pieces of the shell. So I have more disorder. So any spontaneous process, the entropy of the universe will increase for that spontaneous process. That's the second law of thermodynamics. So in other words, for a reversible process, the change in entropy of the system plus the change in entropy of the surroundings is just going to equal 0. So what I do, if I have my water and I place it in I pour water in an ice cube tray, I place it in the freezer, makes ice. But then I do the reverse process and I take the water out, take the ice out of the freezer, get water. Ultimately, the net change, my delta S, is just going to be 0, because ultimately all I've done was just reverse what I just did to begin with. So those processes are like equal in magnitude, but just opposite in their direction of heat flow. So ultimately, the change in entropy of the universe is just equal to 0 for a reversible process. For an irreversible process, though, I'm going to have my entropy is going to be greater than 0. So an irreversible process, I can't go back and undo what I've just done. Boltzmann. We've heard about Boltzmann before when we were talking about kind of kinetics and thinking about how molecules are moving on a molecular level. So Boltzmann described the concept of entropy on a molecular level. And for that molecular level, let's talk about, I guess, these arrangements here. So I have, in part A, I have 2 flasks that are connected by a stopcock. And I have 2 molecules, one's colored red, one's colored blue, and ultimately, all of them are over here on the left side, and the stopcock is closed. If I open the stopcock, a couple different things can happen. I could have the red one stay in this flask and the blue one go in this flask. So I can see that here. Red stays here, blue comes over here to the evacuated flask. Or the opposite could happen. I could have the red move into this one and the blue stay in the original flask. Or maybe they don't move at all. Maybe they just both stay in here and this one just remains empty. Or maybe both of them move into that evacuated flask, making this one evacuated. So Boltzmann says that there are new arrangements that can happen. So entropy can happen at a molecular level. And Boltzmann says that there's something called a microstate. And